Hello everyone, welcome to recitation number 6. Technically we already had this one on campus. This is just an offline recording in case you want to revise the material or for some reason you missed the session. So today's mainly going to be on pumping lemma for CFGs, for context-free grammars. After we're done with that, we'll go a little bit over maybe some PDA questions, some regular expressions, some regular context-free grammars, just so to see different ideas on everything we've learned before. So let's go ahead and start with pumping lemma for CFG. But before we can talk about that, we should talk about pushdown automatas. So if you remember, PDAs, they were the last layer that we added in this automata hierarchy. So PDAs are the strongest machine we have so far. They were strong enough that we were able to break the ceiling of A and Bn. So if you remember, we were not able to do a language, or we were not able to do a DFA or an NFA for A and Bn because, to put it simply, we don't have really any actual memory there. We only have the illusion or the trick of having states, so we can kind of answer some questions. But with PDAs, we actually do have some memory and actual stack. So if I get the string that is 3 A's followed by 3 B's, simply first we push $1 into our stack. Because I don't have a function that tells me my stack is empty, I have to push $1, so that way when I read it at some point, I'll know, oh, my stack is empty. So push the $, then we'll push the 3 A's as I read them. Then when I start reading my B's, I'll simply pop the A's, and now, oh, my stack is empty because I reached the $sign. That means I should accept. So PDA was able to help us solve this problem. But what happens when we introduce Cn? So now instead of reading 3 A's followed by 3 B's, it's also going to be followed by 3 C's too. Okay, if I try to do a PDA for this, where step 1 will add the $, then okay, I'm reading my A's. Now I'm reading my B's and they pop the A's. When I reach the C part, there's really nothing I can do. So that's why for now, this is now a ceiling. So we're going to have to close this back up. We can't do a PDA for this. So at some point, we're going to need an even stronger machine to solve this issue. But for now, we're going to focus more on, well, how can I prove that I can't do a PDA for this? Well, if you remember, a PDA is equivalent to a CFG. If you have a CFG for something, that means you have a PDA. So really, the question is, how can I prove that a language is not context-free? And to do that, we have to go back to the pumping lemma. So it turns out there's actually 2 pumping lemmas. One is for the regular expressions, the one that we learned about before. The other one is for CFGs. So, and they kind of follow the same steps, but there are some differences. So if we want to go ahead and compare, in the old pumping lemma, we'd break down S into X, Y, and Z, whereas for CFGs, we break it down into UV, X, Y, Z. We'll see what that means in a moment, but first let us remember how we used the pumping lemma for regular expressions. So again, this is to prove that something is not a regex, is not represented by a DFA or NFA. So step 1 would be, okay, I'll take some general family of strings that belongs to my language. So for example, I'll say let S equals this. And this does belong to my language since equal number of A's, equal number of B's. And the important thing is that the string that you choose has to be of at least length P, which is indeed the case. 2P is greater than or equal to P. And this just means, hey, don't choose A power 5, B power 5. That's like a specific string. We have to choose something general. Okay, now if I pump up, so we'll go ahead and maybe skip some of the details. When I pump up and I'll say S prime is X, Y squared, Z, I get A power P plus J and B power P. Now, where did this J come from? Well, J is strictly positive. And since we're pumping up Y, the extra A's that we get are from there. So the sizes of Y is strictly positive. That means J is positive. Well, we're only adding A's. Why aren't we adding B's as well? Well, since XY is less than or equal to P, and XY starts my string, at most XY is gonna be in the A part. Like imagine here, you're starting your string with XY. At most it has a size P. P, there's no way it's going to reach the B part. So that's why we're only adding J here, such that J is the size of Y's, or in other words, it's how many A's I'm pumping up. And all right, so finally, P plus J does not equal P. Ergo, this new S that we pumped is not in our language. However, the formula says, or the lemma says, for whatever pumping you do, whether it's up or down, it has to stay in your language, but it's not in my language. I started with S, that abides or the rules. I pumped up, it's no longer in my language. So that's what we used to do before, and it's similar steps here. So we want to do almost similar things here. So step one would be to take a general family of strings, so AP, BP, and CP. We'll call that S as well. However, we're breaking it down to UVXYZ. All right, so the pumping will happen this time not only on Y, but on V2. And we have some new rules. So now VY has to be strictly positive, and VXY has to be less than or equal to P. So if you remember, like the third rule here is what told us where is my Y. So this rule will tell us where will my VY be, or where will VXY be. Since your string starts with U and ends with Z, it's kind of like VXY can be anywhere. Imagine like a sliding window. VXY can be anywhere in your string. So your string is some A's, some B's, some C's. They're all the same number. VXY can be anywhere here. However, it has to be at most P. So VXY could be contained all here in the A part. It could be contained all in the B part. Again, like because U is at the beginning and Z is at the end, VXY can be anywhere. And it could be here, all in C. Now the cool part, or the other part, is, okay, VXY could actually start from the A zone and end in the B zone too. Or it can start in some B zone and end the C zone. These are all the cases that we have where VXY could be at. Why? Because it's a sliding window. It can be wherever it wants. However, there's a rule where it's at most size P. So I don't have a case. I don't have a case where I start in A and end in C. That's just not possible. So VXY can start in A and end in C. Because if that were to happen, okay, I'm starting in A. I have to then travel through all the B's and then end up in C. But I have P many B's. So that means VXY has to be strictly greater than P. That breaks this third rule, so it's not possible. So two things to take into consideration. VXY could be anywhere, but it has to have a size P. Okay. We keep going. All right, but since we have all these cases, now we're gonna have to prove all of them. So unlike before, where we only really had one case, here we have several, and we have to go through all of them to prove that it's not CFG. Like before, there was only one case, but that's because we structured it like that. Like I could have, for A and B, and I could have chosen a string S, that's AP, BP, or A half P, and B half P. And if we try to ignore for a second that P could be odd or even, if we ignore that for a moment, this is an acceptable string. It has a size at least P. It belongs to my language. However, there are now several cases. XY could be all in A. So it could be all here. Or it could start in A and go all the way to B. That's possible this time. So you'd have two cases. You don't have a third case where it's all in B because XY has to start your string. So yeah, this would not be wrong, but this would be a bad choice, because why choose a case, or why choose a proof where you have to prove two cases when you could only do one like we have here? Okay, so now let's go ahead and actually prove the pumping lemma for A, N, B, N, C, N. So Again, I take some string s. It's a family that belongs to my language. All right, so case 1, we said it's all in A zone. So how would that look like? Well, if I say S prime is U V squared X Y squared Z, so remember we have to pump both V and Y, that would give me AP plus L plus K BP CP. So the things that I'm pumping up this time are L and K, such that L, say L is the size of V, and K is the size of Y. So V is getting pumped up, Y is getting pumped up. That's why we get these two additions, and they're all in the A zone, so we're only adding them for A. Now, the important, or why does this not belong into our language? This new S prime? Well, since, back to here, rule 2 says Vy has to be strictly positive. So since Vy, the size of that is strictly positive, that means L plus K has to be strictly positive. Now be careful, this isn't saying that both of them are strictly positive. Like, it's possible V could be nothing, could be epsilon, and Y is everything that we're actually pumping, but at least one of them has to be strictly positive. So either L is positive, or K is positive, or maybe both. But any one of these ors is enough. If both of them are strictly positive, great. If at least one is strictly positive, that's also great, because eventually we'll just simply get L plus K does not equal P. So now, like, oh, it's no longer equal number of A's, equal number of B's, equal number of C's. That's not the case. So that's the first case. Does this mean my language is not context-free grammar? No. We have to go through all the cases. Again, before it was just a coincidence with APBP, we only had one case. But if we had chosen something like this, where we had two cases, we would have to prove all of them for the language to actually not be regular. So now I have to prove all the cases. Well, I don't have to be repetitive though. I could say similarly for case 2, where it's all in B zone, and case 3, all in C zone, all there. It's the same proof, like we're only contained in one area. The difference would be of, if I was all in my B zone, I would have gotten, when I pumped up, I would have gotten something like BP, AP, BP plus L plus K. So the difference would be where you're actually doing the pumping. If I had gotten it in all in C zone, it would have been, well, I'm pumping the C part, right? So BP plus CP. Whoop. No need for the plus, it's like concatenation. Okay. CP plus L plus K. Cool. So now we actually go to case 4, which is kind of different, which is actually really different. So case 4. It starts in A zone and ends in B zone. This is actually different. How would that look like? Well, okay, so we'd have something like this. When I pump, first of all, let's draw how it will look like. So I have some A's, I have the B's, and CP is over there. We're saying I'm starting here and I'm ending here. Well, S prime would be, so I'll pump up once. Okay. It'll look like this. So try to imagine, where do you want to add them? Where do you think we should be adding my pumping? Well, it's in the A zone and it's in the B zone, so there's going to be some addition of A's and some addition of K's. Or some addition of A's and some addition of B's. L and K are just arbitrary variables. However, I'm going to define L and K to be different than before. Before I was saying, oh, L is the size of V and K is the size of Y. Now it's different, such that L is how many, or say L is, I'll do it like this first. I'll say that L plus K is the size of Vy. Okay, makes sense, right? Like this is, if you add them, you get the size of Vy. That's what you're pumping up. However, I'm not saying like before that L is the size of V and K is the size of Y. This is different this time. What I'm saying is that L is how many A's I have in Vy, and K is how many B's I have in Vy. Why am I saying this? Well, we have to be very general. Think about it. All we're saying is that Vxy starts in A and ends in B. But we really have no idea where exactly V and Y are. It's possible V could be all in A, X is all in A, and Y is all in A and goes to B. Or vice versa. Maybe V is in A and V takes some B's and then Y takes some B's as well. Or maybe Y doesn't take anything. Y could be epsilon. However, what I care about is there is some number of A's being pumped up and some number of B's is being pumped up. And we reference those by L and K. So by saying that L is the size of VA, by saying that L is how many A's I have in Vy, and K is how many B's I have in Vy, I'm really covering all these different scenarios where, oh, V is A and B, or Y is A and B, etc. Like all these different cases. We're summing them in this. And very important, in this scenario, L is not the size of V, it's how many A's I have in Vy. However, similar to before, this does not belong to L. Why? What an ugly belong. But why does this not belong to L? Well, same as before, since L plus V, since L, plus K has to be strictly positive, because Vy is strictly positive. So think of the scenarios. Again, this means either one of them is bigger than 0 or both. Well, if L is strictly positive, that means P plus L does not equal K. Oh, sorry, does not equal P. So like this PL plus L does not equal P. So I have now a different number of A's than C's. It ruins it. Or similarly for K. If K is strictly positive, then as well, P plus K will be ruined with P. All right. So this is everything we have here. Does this mean my language is not context-free? Almost not yet. We have to go through all the cases. So I actually have to say case 5, or we'll simply say similarly, or case 5, where I start in B zone and end in C zone. The only difference is, where are you actually doing the pumping? So I'll just write the string. It'll look like this. So S prime after I bump up once, so U V squared. The reason I always write V squared XY squared because I could be pumping down, I could be cubing it. I'm just trying to specify exactly what am I doing here. It'll be AP BP plus L CP plus K. So same thing, it's now like the number, if K was strictly positive, it's the number of C's that's more than the A, which ruins the whole thing here. All right. So finally, after proving all the cases, L is not CFG because we covered all the cases. All right. Now let's talk about this idea. AN, BN versus 0N, 0N. Now we're gonna do one more pumping lemma, maybe not in this many detail, but just so we can understand, make sure we understand the idea. But there's an important idea here as well. So we know that AN, BN is not regular by now, obviously. But what about 0, 0N, 0N? So pause for a moment and think, is this regular or not? Well, it turns out that it is regular. Why? Well, it's equivalent to 0 to n, and 0 to n is simply the even numbers of the even number of zeros. We can draw a DFA for that very easily as such. So I'll only accept if it has an even number of zeros, reminiscent of the first recitation we ever had. Okay, but now I wanna, so the reason I'm specifying this is, what's the wrong way of using the pumping lemma? So before I said AP, BP, and I broke it down. So I said S is this, and we broke down X, Y, and V as follows. So this is when we really dove into the details there. We said, oh, X is some number of A's, Y is some different number of A's as well, and Z is the rest. So Z is AP minus A minus I minus J and BP. So Z is everything else. This is the right way of doing it. This is general cases. So this covers everything. It's good. The wrong way or the bad way of doing this would have been going for specific cases. So if I had said, oh, X is not epsilon, okay? X is epsilon, Y is AP, and Z is BP. If I had done this, and I try to pump up, so X, Y, Y, Z, I'll get A, 2P, BP, which does not belong to my language. However, this does not mean that my language is not regular. Now, I know that A and BN is not regular, but I'm saying this is not the correct way of proving it. You have to go through general cases, because you can always choose a specific case that doesn't work. So like, I'll try to do this for 0 and n. So I'll say, oh, 0 to P. Okay, and I'll say X is epsilon. Y is like some 5 zeros here. And Z is everything else. So Z is 0 to P minus 5. If I try to bump up here, so if I say X, Y, Y, Z, I'll get 0 to P plus 5. And this does not belong to my language, since 0 to P or 2P plus 5 is odd. So it had to stay even to be in my language. So it's not in my language. However, this does not mean 0 to P is not regular. Like we just proved, we drew a DFA for it. It is regular. So when you choose a specific case, that's not the way to go. You have to first choose a general family of strings, then go through all the cases. If it happened to be one case, great. Or if it happened to be 5 cases, you have to go through all the cases. But even for each case, you have to do something general, like what I was doing here. AP plus L plus K, like this is in general. L and K could be anything. I'm not specifying that L is all 5 A's and K is 2 A's, etc. That would be being specific, which won't work. If I had tried to do the right way here, if I had actually tried to do the right way of proving that 0 to P is not regular by the pumping lemma, that would have looked like this. X is some number of zeros. Y is some different number of zeros. And Z is everything else. So 0 to P minus I minus J. When I pump up X, Y, Y, Z is 2P plus J. So I added J zeros because of Y. This may belong to my language, maybe not. It depends really on J. So it will belong into my language if J is even. It will not if J is odd. And this is really why the pumping lemma doesn't work here, because, or not doesn't work, it's not sufficient to prove that this is not regular, because, hey, not all the cases work. All the cases have to work in general to prove that a language is not regular. So here we can't deduce that 0 to P or 0 to N, like the language, is not regular. Hopefully that gives you an idea on why we're trying to be so tedious with all the cases, all the generality here. But now, let's do one of these in a bit of detail. So you can pause here if you aren't in the recitation. If you'd like to take a crack at these, you can pause here. Like usually I have this pause button because when we started the online sessions last year, to kind of give you an idea that, oh, you should be pausing here to try and solve it yourself. Okay, now we're not going to dive into the details very much in these. We're just going to see the cases. So for example, for part A, what's a good string for here? If I had chosen W equals AP, this might not have been a good case. Why? Because W would be A3P. So it's basically O, A, and then A, such that each of them is P many times. So really, to break this language, you have to pump it up and get a number of A's that's not divisible by 3. Because if it is divisible by 3, that's when it stays in your language. So you have to pump it to a way where it's no longer divisible by 3. However, that's not always possible. It's going back to the 0 to P. If you try, you're not going to always get a guarantee that it's not going to be a multiple of 3. So this is not maybe the best string. Another string would have been AP, BP. This is actually a good idea, because now when I say WWW, or in other words, when I say my string S is AP, BP, and then AP, BP, and one more time. Why is this a better idea? Well, think about it. There will be cases where it's, for example, stuck in the first A zone, right? If you pump this up, you're gonna get some more A's here, and this first W will no longer look like this other W, will no longer look like this other W. So this is a good choice. Well, what are all the cases that I have? Well, case 1, all in some A zone, as we just mentioned. So it could be the first one, could be the second, could be the third. They're all very similar, so in some A zone. Case 2, all in some B zone. This looks like a case 3, so case 2. Case 3, what a horrible 3. So case 3, all in, all right. So the case 3 is actually interesting. So we covered all in A, we covered all in B. The only thing left really is I start in some A and I end in a B, right? However, the choice of words is really important. If I say starts in A zone, and ends in B zone, that's not enough, right? Because if I read this, basically what you're telling me, okay, I start in this A and I could end in this B, but it's not possible, right? If I start in this A, there's no way I'm gonna reach this B because it's too far. Vxy at most is P many, so I can't really cross all the way there. So it's what we're actually trying to say here is it starts in A zone and it ends in an adjacent. Okay, adjacent. I really spaced this badly. In an adjacent B zone. All right. So I'm saying, oh, I'm starting here and then I end here. Or case 4 is the opposite. I'm starting in some B zone first, and then I end in, let me write this better this time, an adjacent A zone. Okay, now, as I mentioned, I cared about maybe just specifying the cases. However, maybe let's just do one for each, because like even for each case, there are so many subcases. Like case 1 has 3 subcases. Is it this A? Is it this A? Is it this A? Case 2 has 3 Bs. Now I could argue that, so if you do one for case 1, that's like enough. But I could even argue, hey, if you do one for case 1 and case 2, that's sort of like enough, right? And case 3 and case 4 are similar too. So like let's maybe call this a subcase of case I, where it's all in some zone, and this will call it case J, or double I, where I'm in some, where I'm in one zone and I stretch to the adjacent one. So case I, say we'll specify all in the second A zone. So we could have chosen the first, but like the middle ones are usually picky, kind of annoying, right? So I'm going to choose an annoying one, not a comfortable one, so you can see how that looks like. But if you chosen the first one, it would have been fine. And said, oh, similarly for all the rest. So all in second A zone. When I pump up here, so S prime is U V squared X Y squared Z. It looks like, all right, AP, BP. I'll just write it out all first. Think about it. Which zone or which part am I pumping up? By leaving the space, I might give it away. But I'm literally saying the second A zone, right? So here is where I add, oh, some L, some K. Like it's very similar to everything we've done before, right? Like when you solve one of these, when you solve one of them, you kind of solved all of them. Maybe not all of them. Okay. Well, since this does not belong to my language, since L plus K is the size of Vy, which is strictly positive. So AP BP plus L plus K is not going to equal AP BP, which ruins the whole format of that I have 3 equivalent strings next to each other. Similarly for everything else, whether it's the same A zone or like a different A zone or maybe some B zone. For case 2I, I start in some place and I end in another. Let's focus maybe on the first part. So I start in the first A zone and I end in the other one. Whew. So start in first A zone and end. You get the idea in an adjacent one. So how will this look like? So I'll write it over here. We'll get S prime is uv squared x y squared z. And it's going to be AP plus L, BP plus K, and then AP, BP, AP, BP. However, same as before, we're going to be saying that L is how many A's I have in Vy, and K is how many B's I have in Vy, because who knows how even more subcases we get there. So this does not belong to my language, since L plus K is strictly positive. Okay. And in short, yeah, the whole thing will not be context-free because for all the cases, it just fails. Okay. You can try to figure it out for all the rest of the cases, or for, whoops. You can figure it out for all the rest of B and C. I'll just maybe give a family of strings for it. So for this one, we could maybe choose, hey, 1p, 0p, and then the multiplication, and by m, p squared. Now, I could have chosen here 2p, and then the multiplication would have been 2p squared. That's fine, but there's nothing telling me that n and m shouldn't be the same, so I can choose them. Here would have chosen, hey, 0p, hashtag 02p, hashtag 03p. Now, I know that we're saying prove that they're not context-free, but you can kind of get your own intuition on why, right? Like they're all like, oh, I have to read p ones, then I have to pop them, then what am I going to do with p squared? It's not there. So intuition-wise, it's not there. It's not going to be context-free. However, I want to focus on one case because it was pointed out in class that's actually a bit different than the cases that we've seen before. So I want to focus on the case where I start in zeros here and I end in the ones here, because this one is actually kind of cool. So I'll say 1p, and zeros, then ones. Here I have p many, here I have p squared many, and that's a 1 here. Okay, now why is this actually kind of different? Because if I start here and I end here, it's obvious that this is a case where it should fail, right? Like I'm starting here and I'm starting here. But when you actually try to do it, when you actually say S prime is u v squared x y squared z, when we actually do it, all right, so I'm going to get 1p, 0p plus L, and then 1p squared plus k. To prove that this does not belong into my language, I have to prove that p into p plus L is different than p squared plus k. I have to prove that. I have to prove that p squared plus pl is different than p squared plus k. So basically, I have to prove that this does not equal this. And this is kind of tricky because we've never seen this before. Like before, it was all straightforward. Obviously here, obviously, p plus L is going to be different than p. This is obvious if it's strictly positive. However, here it's kind of different. So we're gonna have to make use, I think, of part 3. So part 3, we'd usually use this when I want to know where my vxy is. And we usually always relied on the second rule to prove that it's no longer in our language when we pump up. But in this scenario, we're actually going to rely on the third rule too. Because vxy at most is going to be p. So that means, let's say, so that means lnk at most is going to be p. So obviously that k at most is going to be p. Like in the scenario where L is 0, at most k is going to be p, right? But think about it. There's no L that you can plug in here and no K that you can plug in here that makes the whole thing equal. PL can't equal K. Say that K took all the size and it was P. Well, if K is P, that means L is 0, so 0 does not equal P, because obviously the pumping length has to be strictly positive. I'm not sure if it's in the lemma, but that makes sense to me. Well, think about any other scenario where K is not at most P, it's something else. Well, if it's something else, it means it's P minus 1, but here you have something that's at least P times 1, right? Does it make sense? If K is P, like at most, that means L has to be 0, so 0 does not equal P. If K is anything else, if K is strictly less than P, let me actually write it here. If K is the other scenario, okay, it's not exactly P, it's anything less than P. That means L has to be something else, right? If and L is strictly positive, that means O. PL is definitely gonna be more than K, right? So like this is one case, this is another case, maybe a third case. Like what if, again, if one of them is 0, well, 0 is not gonna equal something that's strictly positive. So if K or L is 0, one side will be strictly positive and the other 0. Now this may be I hope I covered all the cases. I hope I didn't specify some case, because that would lead to the issue that we mentioned before. But I think these are all like the different cases of values P and L could take. Now maybe we don't need this much detail. We could have just said, oh, there's no way P times L will equal K. So this is like 1, 2, 3, etc. So it's a really like cool case that happened here. Because in this scenario, I think if we try to do it here, we would have gotten the whole that, oh, this P is not going to equal 2 times, or this whatever, when you add something here, it's not going to equal twice what's here. So this would be falling back to the easier or more straightforward ones. Okay. That's it for CFGs, and maybe for pumping lemmas in general, or the pumping lemma for CFGs. We're still going to see a CFG here. But first, let's see PDA again. So last time we or the time before that, we kind of drew 1 or 2 PDAs. I hope we could have drawn more, so definitely do try to solve more yourself. The recitations are not enough. They're just to try and understand the general idea, and hopefully you yourself can solve more and understand more. Like now, okay, with pumping lemma, if you get a question that tells you to prove that something's not context-free or not regular, okay, you can go through all the steps. Or if you're given a proof that's strong, you can kind of maybe point out where it's strong, or you didn't take the correct string, or you specified a case, or whatever, or maybe you're asked to list the steps of the pumping lemmas. How do you prove something? Is there a step that's missing, etc. So we try to, with the recitations, we try to understand the general idea. We try to practice as many problems as we can, but obviously you're gonna have to try to practice as much as you can yourself. So with the PDAs, I don't think we drew enough, so do try to draw some maybe PDAs yourself, or solve general PDA questions. But anyway, for this question, for this PDA, what we want to do is understand it. So we created a couple of PDAs before. In this one, I want to try to understand what's going on here. You can pause and try to think about yourself. However, maybe a hint. Go with me, maybe a hint. What is this PDA doing? So I know the first part is saying, does it accept the string? The second part is what is asking for the language. But before we dive into that, can I understand what's going on? Can I break it down into steps? So what is step 1 doing? When I go from here to here, I'm pushing $1, right? So that's what we do. I don't have a button. I don't have a function that tells me my PDA is empty, my stack is empty. I have to push $1 there. Step 2, what's going on in Q1? Every time I'm reading an A, I'm pushing an X. So read A, push X. What's the third step? So it's this from Q1 to Q2, it's just a free transition, so that's nothing. The actual third step is, okay, I read an A, I push a Y, which is really interesting. It's weird and interesting, like 2 choices, because these are consecutive. Will you read an A and push an X, or will you read an A and push a Y? Like, it's a choice you have to do. So this is interesting. 4, just read a D, simple enough. What is step 5? Aha, this is different. Okay, let's try to read that. Read a B, pop a Y, and push a Y. So it's kind of like you're just checking if you have a Y. You're not really popping it yet. But when you go back, read an A, pop a Y, push nothing. So really, what went on in this circle? When you started at Q3, you went to Q4 and you went back. What happened? What did you read? In total, you read a B here, and then an A here. So you read BA. In total, what did you pop? Here I technically popped a Y, but not really. I pushed it back, and here I popped one Y. So read BA, pop Y. What is going on? For every Y you have, you're going to be popping a BA, which is kind of maybe related to step 3, right? It kind of feels like step 3 and step 5 are going to be related. Like for every A that you're replacing with a Y, it's actually going to be a BA. All right, what is step 6? So I reached the Q5, Q6 area. It's similar. What's happening? I'm reading a C, and let's go very far. So I read a C, and we're going back and we're reading another C. So here we're reading CC. What am I actually popping though? I'm not really popping this X. Here I'm popping it, so pop X. So again, it's the choice all over again. Do I want to read BA or do I want to read CC, depending on what I replace the A with? Okay, so now we can actually try to solve this. All right, so part A. Do I actually accept this string or not? Well, think about it. Like we can use our minds and go ahead in the future. Here I have a BA, here I'm gonna have a BA, and here I have a CC. It feels like this BA, according to the steps, is popping some Y, and this BA is popping some Y, and this CC is popping some X. And at the beginning, I have 3 A's, so I just have to carefully replace them with what I need. So I'm in Q1, so first you have to replace with an X. You can't replace the Y first. When you reach the Y reading area or pushing area, you already passed the X. So I'll need to replace this A with X. So imagine your stack, $1, I pushed an X here. Then these 2 A's, all right, I have a Y here and a Y here, which is really cool because now what it's entered in my stack, it's entered in reverse, right? So when I actually reach this BA, all right, I pop the Y. When I reach this BA, I pop the Y. When I reach this CC, I pop the X. I'm left with $1, so yes, I do indeed accept. Because you pop the $, you reach the accepting state. Cool, we do accept it. However, this is kind of understanding how we accept it. Maybe the actual proof, like this would be a cool, if you can explain it neatly in English, I think it would be acceptable. But like the formal proof for it, which I don't have memorized, I'm pretty sure you remember in class, there's a formal way of reading how a PDA is, what's happening in a PDA. Like you'd have your string AAA, DBA, BA, CC, right? And like you'd say, oh, right now I'm at Q0 and I've read nothing. Then you go to Q1. You still haven't read anything, but in your stack, you have $1. Then you go to, then you stay in Q1, right? I stay in Q1. So far, I've read 1A from my string. And I push $1 and then an X. Then I go to Q2. I've only read the A so far. So going from Q1 to Q2, that's a free transition. And I have $1 and X my stack. And you get the idea, right? Now I've read AA. I'm still at Q2, but in my stack, I have $1 and an X and a Y and so on eventually until you end up in the accepting state, which is you've read the entire string and you're at Q7 and your stack is empty. Okay, cool. So I'm not sure if it's exactly like that. You make sure you revise your class sessions. But now, what language is L? Which language L does the given PDA accept? Well, I could maybe go through the steps, right? Like, what are we doing? What are the big blocks? Here, I'm reading some number of A's, so I'll say AI. Here, I'm reading some different number of A's, I'll say AJ. Here, I simply read the D. This loop, mini loop, I'm reading BA, which is equivalent to the Y's, so that the AJ's, the second A's. So I'm reading BA's. How many? As many AJ's are read. So the J's. And finally, CC is equivalent to the I's. Very cool, such that I and J are greater than or equal to 0. Now, if I and J are 0, does that mean D gets accepted? It does. Like, oh, if I only have the D string, does that mean I get accepted? Well, yeah, I push $1. I go here, free transition. I read the D. I go here, free transition, and then I just pop the $. So yeah, indeed, it does get accepted. Cool. Now let's try and do part. Whoops. Let's try and do part C, which is the CFG. Okay. Now, again, I've mentioned this before, but try to be comfortable with the formal way of how we define stuff. Like I've mentioned this for the DFAs. Like, oh, you have some set of accepting states. You have a starting state, etc. For the grammar, it's similar. Here, I have my variables. I have my constants or my terminals. I have the list of rules. That's right here. And I have my starting variable. So X is what starts the whole thing. So which language does this context-free grammar accept? Well, you're going to have to think about it. So you can pause here and try to think about it. Okay, so how would I solve this? Well, in class, I noticed that a lot of you tried to either think of specific cases like, oh, X goes to epsilon, so I generate the empty string, which is correct. However, it's usually better to try to think of general cases, like a general solution, a general language, then you can focus in on these specific cases if they are there. Because maybe if you come up with a general case, it might cover your specific case. And the other thing I noticed, well, right away you went to the hard case, which is, all right, I do some X and I do some Y. But if I notice, there are rules where I'm only on the X. So do a case where, okay, only for the x's, if I only use the x rules. So x is being replaced by 1x1. It's then being replaced again by 1x1. This reminds us of what? Oh, I'm going to have here some n1s and here some n1s, right? This is this rule. And then this x, I can replace it with either 1 or epsilon. Well, if I replace it with 1, that means I get 1 to n plus 1, which is the odd ones. If I replace it with epsilon, I get 1 to n, which is even. Well, I can generate the odd ones. I can generate the even ones. That means simply I can generate all ones, right? I can say 1 power n, or maybe I could say 1 star. That would have been fine too, like any number of ones. In this scenario, it's the same thing. Case 2. Again, I don't want to mix the two variables just yet, because if you notice, I can go from x right away to y, and when I go to y, I can't go back to x. So let's just focus on y. And you'll notice it's the exact same rules, but instead of 1, it's 0. So it's also as if I'm saying, oh, 0n, n is greater than or equal to 0, or like 0 star. Obviously, this n is different than this n. Finally, case 3, it's when it's actually being mixed. But again, this rule here, like if we can notice, this rule is terminating. So if I reach this rule, it's like my string ends. So I have to use this rule to get some 1s. Then I go to y, and when I go to y, I can't come back. All right? So this first rule, same as before, x, being replaced with 1x1, being replaced with 1x1, etc. I have some n, and then finally I'm replacing it with y, and this y will have some n's here, number of ones, equivalent, and I can replace it with, as before, like 0n, 0 star. Not exactly 0n, I'll say 0m, right? Because it's not necessarily the same number of ones. So case 3 is you'll have some zeros in the middle, an equivalent number of ones on the left and right. So you really have these 3 cases where n and m are positive. There's no relationship between 1 and m. Okay. Now, some of these cases may be inside each other. Like if you notice, case 2 is kind of inside case 3, right? Like if n was 0, you're left with 0m, which is like this 0n, like some number of zeros. So case 2 is inside case 3. However, case 1 is not inside case 3, because if I take this m to be 0, I'm left with only 1, 2n, which is the even ones. But however, case 1 can also generate for me the odd ones. So that's enough. I don't have to be so optimal here. I can simply say, oh, these are my 3 cases. So this would be more maybe understandable than if I just gave you case 1 and case 3, even though they might be equivalent. Okay, cool. So we were given some PDA, we were given some CFG, and we were able to understand both. Now, actually, in class, we were brave enough. So I only showed this part C because I didn't think we'd have enough time in the actual on-campus recitation, but we did. And we were brave enough to see that this part C was not actually a part of the previous problem. It was actually its own problem. So what is this problem on its own? So we already solved part C, but let's see what's part A and part B are. I think they're really cool. Provide a context-free grammar G, such that, again, remember the formal way of representing it, such that it generates the language of palindromes over some alphabet sigma. So I'm given some alphabet sigma, and I have to prove, or I have to, in general, write a formula or a grammar that generates it. Now, no need to be really confused here. Like we haven't seen this before. But what is really happening? You have some alphabet, right? What is this alphabet? It's made up of some elements. E1, E2, E3. Somebody in class pointed out my E's look like L's, which I agree with. So I have some E's all the way maybe to En, such that the size of my alphabet is N. So this is your alphabet, but like instead of specifying 0, 1, or ABC, we're just saying there's some random elements, some arbitrary elements. All right, S, what can it go to? So you can pause here to maybe try and think, well, what could my language be? Okay, Simply, it's, well, E1 is E1, right? Like, for the first element, it has to be symmetrical. E1 S E1. Like we've seen this before, we've actually done this grammar, if you remember, where we said S goes to 0 S0 or 1 S1. It's the same thing here. Before, my alphabet was just ones and zeros, whereas here it's arbitrary elements. So, or E2 S E2, or E3, or all the way till EN S EN, right? However, I do need to terminate. How will I terminate? Before we'd ended with like, or epsilon, right? And that could work here. If I end with an epsilon, like, oh, you're building symmetrically your palindrome, and then you end it with an epsilon. However, if I only end with epsilon, if I can only terminate with epsilon, I'll generate the even strings only, the even palindrome strings. So I'll need some more rules. I'll say or E1, or E2, or all the way to EN, right? Makes sense. These rules that I added at the end are very important. They are what generate the odd palindromes, right? So here we'd have an actually or 1 or 0 as well. Cool. Okay, so that's part A. We gave them a grammar that's the language of palindromes. However, part B is saying, prove it. Like, how can we know that the language that you gave us is actually the language of palindromes? You have to prove it. And it's at this point that I mentioned, well, what's a way to prove something? What's something that we know from 211 that can prove it? Well, remember, so far we've used counterexamples, we've used counterpositive, we've used a bunch of stuff. What's something that we can use here? Well, to prove something, and by the way, we've also used contradiction, right? Like everything with the pumping lemma is contradiction, where we assume that something is regular or something is CFG, and then we prove otherwise at the end. We reach a contradiction. Well, something from 211 is induction. Induction to prove something. And what am I trying to prove here? Using induction, we will prove that we can generate a string, a palindrome string of any length. So a palindrome of any length. Like, think about it. If you're able to prove that you can generate a palindrome of any length, that means you generated, you made a language that does that generates all palindromes. Okay, so how does the induction theory goes? Well, something like this. So step one would be to take a few cases, right? So we'll say something like case 0. Actually, let me maybe get what we wrote before. Okay, so you go up and you come down. All right, so I have my grammar here at my right, and I'm trying to prove that I can generate everything. So let's say a case where n is 0. So n is going to be the length of my string. Do I generate all the strings that are of length 0? Do I generate the empty string, in other words? Yes. I have the rule s goes to epsilon. So I'm able to generate the empty string, so I'm able to generate all the strings that are of length 0 that are palindromes. It happens to be only 1. Let's do a few more. Case n is 1. Do I generate all the strings that are of length 1 that are palindromes? Yes. S is E1, E2, etc. These rules all generate all the palindromes of length 1. One more, do I generate all the strings that are of length 2? Yes, I do. I simply first go s goes to some ei, s ei, like some random arbitrary character in my alphabet. Then I replace s with nothings. With the epsilon, I'm left with ei, and the length of this guy is 2, so I'm done. And so on. Like, you can think about it. If I wanted to do it for n equals 3, I'd do this. Then I'd replace s with any random. Like, actually, let me do it, because it, just so you, let me see if you know what I should do here. If it was case 3, all right, first s, I'd replace it with ei, s-ei. Then tell me, or like pause, what do you think I should replace s here with to generate any string of length 3? I should replace it with not ei again, because that would make all the characters the same. I replace it with some ej, right? Like, j could equal I, but not necessarily. And like the length of this guy would be 3. All right, so that's step 2. That's step 1. Step 2 is usually you just assume it's true for n equals k. But what I'm actually going to do, because I actually need this, another assumption would be assume up to n equals k. It makes no difference in writing it. Like, you could assume this or assume this. The difference is, if I'm saying for n equals k, that means I can generate. Let me actually write this. So, so what does assuming for n equals k mean, and for the other one means? Go away. Do you have some idea? The first one is saying, so when it's n equals k, I am assuming I can generate a string of, I can generate a palindrome of length exactly k, right? However, this is when I say n equals k. However, with the other one, n up to n equals k, so it's like saying I am assuming for n is less than or equal to k, so I can generate any string, any palindrome string of length less than or equal to k, which is more powerful. Now, like, you can assume whatever you want. Usually we only assume for n equals k, because that's all we need. But in this case, we'd actually need both of them. We'd actually need the stronger case. You'll see why in a moment. So step 3. Okay, what am I gonna say here? I have to prove it. So now it's required to prove that I can generate a string of length n equals k plus 1. Can I generate a string of length k plus 1? Well, let me try. S, I'll replace it first with some random arbitrary number, right? Then what should I do? Using my assumption of step 2, I'll replace this s, because remember, what is step 2 saying? I can generate any palindrome of length less than or equal to k. Well, what do you think? What should I replace s with? Like, I'll replace it with some string w, right? But what should the length of w be? Well, such that w is a palindrome, and the length of w is k minus 1. Why k minus 1? Because now when I check the length of ei, w, ei, it's gonna be the two i's, so 2 plus k minus 1, which is k plus 1. So I was able to generate the string a string of length k plus 1. And this is any general string of length k plus 1, which is really cool. That's why I needed up to in mind, up to k. If I had only said nk, I would have had to replace it with some w of size k. I would have had to do this, replace it with k, and then here I would have ended up with n plus 2, with k plus 2. Like I would have overshot it. I would have generated a string of length k plus 2, not k plus 1, which is why I had to choose w to be k minus 1. And again, just to be careful here, s, when I replaced it with EI, I used my grammar. A rule from a grammar, like this is my grammar, I can do that. But however, the second replacement was done by induction. Like, okay, like you're saying your grammar can generate any string of length, any palindrome string of length, up to k. Well, I just did that. I simply replaced this s with this w, such that w is a palindrome of length k minus 1. Like, this is the whole point of induction. I can do this recursively, right? I don't have to actually worry about the step. Like, just imagine there was a series of step here in the by step 2. There was a series of replacement that ended up with a w such its length is k minus 1. All right. Now, there is like maybe one worrisome thing, which is it an odd palindrome? Is it an even palindrome? Well, just to be safe, we could have also proved it for n equals k plus 2, right? Like if I prove it for k plus 1 and k plus 2, like, okay, I would have generated even and odd. There's no problem with the proof. But this is good enough for me for now. Okay. Now, it's at this point in class that we covered all the main ideas, and we ended it with some true or false questions. So let's see these. Is every subset of an irregular language irregular? So as I go through these, if you want, you can pause and think of the question. Is every subset of an irregular language irregular? Well, the question is saying you have some like imagine you have L2 and you have L1 is subset from it. And they're saying, oh, if L2 is irregular, that means that L1 has to be irregular. This is what they're saying. Every subset of an irregular is also irregular. But not necessarily. Because think about it. If L2 is irregular, like A and Bn, so I'm saying this is not true. Well, to prove it, I'm going to have to come up with a counterexample. So I have to come up with some language L2 that's actually irregular and something that's subset from it that's actually regular. Can you think of something? Can you give me a case where, oh, this is regular and it's subset in this that's irregular? Well, how about, well, something that was given in class was this, language AB. Like literally the language that only accepts the string AB. Is this regular? Yes. Any finite language is regular. Here is an automata that accepts AB. So it is definitely regular. Here it is, AB. Or I could have chosen the empty set. The empty set is also regular, right? Like if we were talking about AB, I would have done this. If we were talking about any general set, I would have looped it like this, where epsilon is like your alphabet. Sorry, not epsilon, this is sigma, right? Or like, hey, if we want to be like, if your sigma was E1, E2, N, like you'd loop it like this, all your elements. All right, so yeah, this is not true, it's false. By counterexample. What about this one? If R and S are regular expressions, then these two are equivalent. R followed by SR star or RS followed by R. Okay, now for some intuition, I'd say, okay, like see what this becomes. So R followed by SR, followed by SR, followed by SR, and like indefinitely. However, this one is saying, oh, RS, 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 indefinitely, but then at the end you end it with an R. It feels like they are the same, all right? Whoops. Yeah, like at the end here, this one ends with RSR and this one ends with RSR2, right? Like as long as for how many of these have you put as well here, it's the only difference is all here you're starting it with R, whereas this one you're ending it. So this is intuition wise, and this was the best thing I had. But a few of you in class mentioned, hey, maybe in general we could make a DFA for it, or in general we can make an NFA for it, right? And yeah, that would be a more formal proof, or maybe the recursive definition of regular expressions that would help us to prove that they're equivalent. But yeah, this is good for me. So they are true. They are equivalent. What about here? They're not going to be equivalent, right? Maybe we've seen this before, and some of you were saying, hey, I'll replace L with LLL and things like that. So basically, L star is like you're getting OL concatenated with L, concatenated with L, etc., and so on. Whereas this one is saying OLL concatenated with LL, etc. So you try to do it this way, which is maybe you'll get somewhere, but this may be very difficult to prove in general. So why not take a counterexample? In counterexamples, it's okay to be specific. When you're trying to prove something, however, using the pumping lemma, we have to go through all the cases. But with counterexample, that's the whole purpose. Example, being specific. So I'd say OL is, we did it for A, we also did it for 0. Let's say we want to do it for A. Or hey, let's be a bit different. I'll do the example you mentioned in class, which is the 0. So 0 is regular, right? It's a regular language. It only accepts the string 0. L star is like 0 star, which is 0 star. It's also regular. Here's a, I don't know why I'm saying regular. Like yeah, so the language has to be regular, obviously. So we started with a regular language, but the question isn't about regular. Are these two expressions equivalent? Well, what is L concatenated with L? It's 0 0, and it does have a language as well. We just accept the string 0 0. What about L0 L all star, which is like 0 0 star? This is the even zeros, so this will only accept even zeros. So obviously these are not the same, right? Like these two are not equivalent because one is all the A's, whereas the other is just even. Sorry, one is all the zeros, whereas the other one is only the even zeros. So they're not the same. So this is gonna be false. 2 more, and we're done. This one right here. X, Y, X reverse. Is this the irregular language? Now, if I try to read this, like we've kind of seen this before, right? Like when we had XX reverse, this is obviously not regular because XX reverse is like the palindromes or like the even palindromes, right? Anyway, like it's some sort of palindrome, that's a problem. So this won't be acceptable. This is not regular. Should I mention even? Yeah, why not? We'll say even palindromes, why not? So this is not regular, but imagine like you have something that's already not regular, like you're sticking a Y in it. It feels like this is right, something like, imagine, 0, 0, 1, then some Y in the middle, and then later you have to memorize 1, 0, 0, right? Like imagine it's like the palindromes with something sticking in the middle. So it feels like it's even worse than the palindromes, right? So this is not regular. However, it actually is regular. So this is weird. Why am I saying it's regular? ask yourself this question. You can pause here and ask this question. Is this really equivalent to this? So is it really the language of palindromes with something in the middle? Or is it something different? Okay. So I'm going to name this language L. Do you agree with me? Like, I can break down this L into a bunch of other languages for different values of x. Like, I can say, oh, when x is, say, 110, it's the language 110, some y, 011. Union with all the different other possibilities for x. Do you agree with this? Like, this is now is 10, y, 01. Like, this is basically what this language is. Like, oh, all the different values for x. When you union them, you'll get x, y, x reverse. And like this y here is arbitrary. It could be anything. That's the trick. Y could be anything. Y is in sigma star. So what happens when x is nothing? X is epsilon. You're saying y such that y is anything. Union a whole bunch of all the other different values for x. But what I care about is this x. If you're saying y is in sigma star, this is like saying, oh, when x is epsilon, you can do anything. You can generate any string. Sigma star union anything will get you sigma star. Like, sigma star is your entire universe. It's any string you can do, depending any string you can produce using your alphabet. So this is equivalent to sigma star. And sigma star is sigma star is obviously regular because here is a very complex PDA that accepts anything. Right? You just make one state, you loop over yourself, and for any alphabet, this is not epsilon, this is sigma. So for anything in my alphabet, I'll just stay where I am and accept. Obviously, this is right. So the trick is, imagine when x is nothing, you're left with y, and y could be anything. So yeah, you get everything. When x is nothing, y can be anything, you get everything. So it's actually true here. So be very careful when you read the problems. All right, last one. If L is regular and F is finite, that means the union must be regular too. L is regular. So imagine L has some machine that generates it, right? F is finite. So F is made up of finite strings. S1, S2, up to Sn. It's finite. Just like before, what I was doing here with, oh, if I only have the string 0, I can create a DFA that only accepts 0. We can do the same thing for F. Simply, oh, I'll make a machine MS1 that only accepts the string S1. I can physically create that, and then I'll make machine M2 or MS2 that accepts 2. And so on. I can keep creating machines MSN that accepts SN, and then I'll make one big starting state that goes to all these machines. This is something that accepts this is why finite languages are regular, because you can make a machine for it this way. Then I'll make one bigger machine that goes to the start state of L, or to the start state of this guy. This is actually the start. I don't know why I said epsilon. Yeah. So yes, it is regular because you can make this machine that accepts the whole thing. All right. Now, nobody's here, so I assume nobody's going to ask any questions. Maybe I'll ask a few myself. Is this enough? No, like, try to solve as many problems as you can. As always, like right now, chapter 1 and chapter 2 should be on Moodle, so you can practice those. Make sure you revise your lectures, all the formulas, all the proofs, etc. Yeah. Again, recitations are to try to understand the idea. You have to practice as much as you can yourself. And hopefully that will be enough. So good luck on Saturday for your exam, and see you, I guess, on Saturday.